So this is chapter 17b, worked problems. I've got to give you a couple of problems that I have for you that you can skip, or one that you can skip anyway. So I'll get to that in just a minute. So I just want to mention here before we go through these that the main two things you need to know from this chapter would just be how to do KSP problems. Either to find a KSP if you know what the solubility, what they call the solubility is, or if you know what the solubility, or sorry, if you know what the KSP is, to find the solubility. So you're just working backwards, so back and forth. So what I've done is I've abridged the set that you have that you can download from online. And what I did was I took out the problems that we will be doing similar problems to them today to keep these videos as short as possible for your sake and mine. All right, so having said that, I took out some of the multiple choices, so when you get to those, if you realize, well, I didn't talk about those, well, it's because it's just basically going to be done the same way that we've done something in this set. Also, for problem 16-109, you can just completely skip that one because that one's a little bit much. So 16-109, it's a 3-slide problem, just forget it. And also 17-111 or /111 is very similar to the last problem we'll do, so it's just got numbers that are different. One of the, instead of being silver chloride, it's silver iodide, but it's done the same way. And then there are 2 parts to it, but it's basically going to be done the same way as the one that we'll do last. Okay, so that's 16-109. You can completely forget about that one. 17-111, it'll be done the same way as the last one that we do. For the test that's coming up, you'll want to go through the rest of these problems, and I think what's going to happen is once you do them, even if you don't understand this stuff, if you can just make yourself go through these about twice, then I think you're going to start to understand what's going on. Most of these are just going to be done the same way. There's a question sometimes about whether you put a number in or whether you put X in. Okay, so the rule for that is very simple. If they tell you what the solubility is, then you just put it in. So you don't have to use the X's, right? Otherwise, if you don't know what it is, if you're trying to figure out what it is, you have to use X. And usually the variations are going to be like X times X equals KSP, or X times 2X quantity squared equals KSP. Sometimes there's a few cases where it's 3X to the 3rd power equals KSP. But it'll usually be one of those 3 choices. So I'll try to make this as simple for you as possible. All right, and then again, the ones that are not there in this slideshow have been removed because they're similar to the things that you've already got. Let me go ahead and go to the next slide. Next. Okay, so whenever you have a problem where they give the solubility to you, and we'll talk about that in just a second, if they give it to you in grams per liter, okay, you want it in moles per liter. Grams per liter does you no good. It's just that sometimes they give these solubilities in grams per liter. So to convert to molar solubility, you just divide the grams per liter by the molar mass. You divide. We have a problem in a little while where you have to come in the opposite direction, because they give it to you, you figure it out in moles per liter, and they want it in grams per liter, so then you would multiply by the molar mass. So you can just look at the units and figure it out. So we'll have to do that for A. We'll have to find, remember C2O4 2 minus is oxalate, so this is calcium oxalate, right? So for A, so we have to find the molar mass for that. So whatever we get when we divide 6.1 times 10 to the minus 3rd divided by that molar mass will be the molar solubility, which is 4.77 times 10 to the minus 5th, I think. I can't advance the slides because I can't get back. So other than that, this problem is very straightforward, these 2 problems, A and B. So for A, if you'll take a look at that, it's calcium, Ca2+, C2O42 minus, when it has its when you put it in water and it breaks up into Ca2 plus and C2O42 minus. And then if you do an ice table, since we don't have anything to start with, it's 0 plus x is x for both. So at the bottom, at equilibrium, we have x squared equals whatever the KSP is. And we know what x is because we figure it out when we're doing what I just said about the grams per liter divided by the molar mass. So, excuse me, it's 4.77, I think, times 10 to the minus fifth. We'll check it in a minute. Squared, and that's all you have to do for A. For B, it's a little different. Again, we don't have anything to start with. We don't have anything but zeros across the top. But for the bismuth, you'll have 0 plus x is x as before, but for the iodide, you're going to have 0 plus 3x is 3x, right? Do you see that? So, and then remember that 3x is just telling you how much the concentration is. Why are we doing x's? Because we don't know the number. Okay, and then remember the equilibrium expression will be the K equals the products over the reactants. So products, in this case the reactant is going to be 1 because it's a solid. So K will just equal the products, right? So it's just Bi 3 plus times I minus to the third power, but I minus is already 3x, right? So be sure you see that. That's the one point that confuses a lot of people. So when you take 3x and raise that whole quantity to the third power, you get 27x cubed. All right, let's move to the next slide. So here's A. All we have to really do for this one is just divide the 6.1 times 10 to the minus third by 128. I mean, the way I have it is equivalent to dividing. And so you get 4.77 times 10 to the minus fifth, and that's moles per liter, right? So that's what we want. And then, since they're both ones, it's 1 to 1 to 1, then we just have 0 plus x is x, so we have x squared equals KSP. KSP is what we're trying to find. So just what you'll do here is substitute in 4.77 times 10 to the minus fifth, which is what we got for x, and then multiply it by itself because it's x squared, right? So if you look at the bottom, the second to last row, KSP is x times x, which is 4.77, e minus 5 times itself, which is 2.3 times 10 to the minus ninth. And that's all you have to do. Next slide. And for this one, it's a little harder. We're going to wind up with x for the bismuth cation, and we're going to wind up with 3x for the iodide. Again, but that has to be raised to the third power. So look at the bottom where it says B, the equilibrium is, and then come down to the fourth row. It's KSP is going to be the concentration of Bi3 plus times the concentration of I minus to the third power. But we don't have those numbers, so we have to use x instead. So for bismuth, it's just x, but for I minus, it's 3x. But because of the equilibrium expression, that 3x has to be raised to the third power, which is 27x to the third. And then when you multiply that by x, you get 27x to the fourth. And that equals KSP, as you can see. So this is just writing what we call the KSP expression. It's just like a K expression. It's just K equals products over reactants. And then just solve for x, and you get at the bottom 8.20 times 10 to the minus 19th. Next slide. Okay, this one's phrased a little differently. So it's dissolving in 1 liter of water, so we're going to have moles per liter if we can convert 0.14 grams of nickel 2 hydroxide to moles. So again, what we'll want to do is divide 0.14 grams by whatever the molar mass is for nickel hydroxide. And then this one will be like the one we just did, in that it's not 1 to 1 to 1, it's 1 to 1 to 2 in this case. So for nickel 2 plus, we'll have 0 plus x is x. For hydroxide, we'll have 0 plus 2x is 2x. And then, of course, that has to be squared. So, again, we're trying to find KSP. So all of these are going in the same direction. We're trying to find KSP. And there's a note here which you can read, which you won't understand if I try to talk about it right now. So I'm going to wait until we get to problem 5, and then I'll explain it then. So number 3 here and number 4, you don't have to worry about doing all the stuff that we're going to do in number 5. In fact, you'll probably never see this stuff on number 5 again. I might ask it on the test, or I may not. But you wouldn't see it on the final. Okay, it's just too complicated. So anyway, we're supposed to find KSP, and we know what X is, or we can figure out what X is. X is the solubility. Now, when they say solubility, what they mean is the solubility for the salt. In this case, that's nickel hydroxide. But usually, it will not only be the solubility for the salt, but it'll also be the solubility for or it'll be the concentration at equilibrium for one of the other things in the products, right? So in this case, it's for the nickel 2+, because there's a 1-to-1 relationship between nickel hydroxide and the nickel. Every time nickel hydroxide breaks up, it produces 1 nickel. So the concentration at equilibrium of the nickel 2+ will equal the KSP, will equal the solubility. So to get the KSP, we just want 4x to the 3rd power, and then it's going to equal the KSP, but we know what X is. In this case, we can figure out what it is by just taking 0.14 grams and dividing by whatever the molar mass is. So let's go to the next slide and see that. So when we divide 0.14 grams per liter by 93, we get 1.5 times 10 to the minus 3rd molar, and that's going to be the concentration here that we're going to call X. So that would be actually the concentration of the nickel 2+ at equilibrium. It's what we would have gotten if we did an ice table, which I've kind of quit drawing those because I'm assuming you know how to do them by now. It's what we would have gotten for the nickel 2+ had we done an ice table. So, excuse me. So if you look at the bottom there, we have 4x to the 3rd power equals KSP, but we know what X is. It's 1.5 times 10 to the minus 3rd moles per liter. So just put that in for X. Substitute in 1.5 times 10 to the minus 3rd moles per liter for X, raise that to the 3rd power, and then multiply by 4, and you get 1.4 times 10 to the minus 8th, which is your K value. Next slide. Calculate the molar solubility of magnesium hydroxide, whose KSP is 8.9. Now this time, times 10 to the minus 12. This time they're giving us KSP and asking us to go in the other direction. So for this one, all we have to do is basically figure out what the, like x squared or 4x to the 3rd or whatever it's going to be for these things that are coming out of the salt, and set that equal to the KSP. So these are really straightforward. But they can be more complicated if they give you a common ion, because you won't be starting with 0. So if they give you a common ion, like if, for example, if you already had 0.1 molar Mg2+, you would not start with 0 plus X, you would say 0.1 plus X. Okay, so, all right, so anyway, back to this. So for MgOH2, we are going to have 0 plus X is X for Mg, and 0 plus 2X is 2X for OH minus, which then has to be squared, right? So it's going to be 4x squared times x, which is 4x to the 3rd power, or 4x cubed, equals 8.9 times 10 to the minus 12. You'll forgive me, there's a lot of allergens in my place here. Next slide. What we're going to do here is use the given KSP to find the solubility. So just set 4x to the 3rd equal to that number they gave us for KSP and solve for x, and that's it. I mean, so these are really easy. And you'll probably get this kind of question on the final exam. Okay, not so much on my exam, but on the final. Remember that on the final, you'll only get about 3 to 4 questions per chapter. So for this chapter, spend most of your time going over these basic problems here. So when you solve 8.9 times 10 to the minus 12th at the bottom here, equals 4x to the third power, you get 1.3 times 10 to the minus fourth moles per liter. All right, now the next problem we're going to do is going to have hydroxide in it, but the concentrations of hydroxide in number 5 will be lower. Now try to catch this, will be lower than the concentration that's already in the water. So remember, water auto-dissociates, and it always has a concentration, at least pure water does, of 1 times 10 to the minus 7th, both for the H plus and the OH minus. So it turns out that for number 5, which let's go ahead and turn to that now, for all of these, part A, B, and C, for all of these, the concentration that we would have gotten had we solved it the way we solved the last two problems would be less than the concentration of OH minus that's already there, which is 1 times 10 to the minus 7th moles per liter. So we have to do this problem differently. It turns out it's not particularly hard, but you just have to be aware of what's going on. So again, you might see this one on your test from me, exam 3, but you won't see this for sure on the final. You won't see this for sure if you take the MCAT. Okay, this is just above and beyond. So what this means is that we have to substitute in. Okay, so before we do this, let's just think about what we're going to have to do to set the problem up. So we're going to write KSP equals concentration of Fe3 plus the concentration, okay, first of all, let me back up. The equilibrium expression will be FeOH3, double-headed arrow, Fe3 plus OH minus, and there would be 3 of those, right? And then the KSP expression would be KSP, which is given, would be the concentration of Fe3 plus times the concentration of OH minus to the third power. You would typically start this off by saying for Fe it's 0 plus x is x, and for OH minus it's 0 plus 3x is 3x. And actually that is the way you do this one, but then what we know the KSP, and we can also figure out what the OH minus concentration is. So I mean, in order to actually do this, I mean, totally, to do this completely from scratch, what you'd have to do is you'd have to do it the way we've been doing it, and then you'd realize when you found x that x is actually like 2 times 10 to the minus 10th, or something like that. And so we'll see it on the next slide. And so that's actually the concentration of OH minus would be 10 to the minus 10th if that were correct, but it can't be right because there's already 10 to the minus 7th OH minus in there. All right, so anyway, what we have to do then is we just have to figure out what is the concentration of OH minus, which we can do that. So what we can actually do is we can rearrange the KSP expression, and we can say that, okay, so KSP equals Fe3 plus times OH minus to the third, but for the OH minus, we already know what it is. So what we can do is rearrange that equation to get the Fe3 plus by itself, which would be KSP divided by the OH to the third. And then we can find the concentration of the Fe3 plus, okay, which is equivalent to finding the solubility for FeOH3, because it's a one-to-one relationship. So what we're actually going to be finding is the X, as usual. All right, so let's look at this. For part A, what's the pH, what's the OH minus concentration of water? pH is 7, OH minus and the H plus are both 10 to the minus 7th. So that's what we're going to write in for the OH minus for the first part. For the second part, if the pH is 5, the pOH is 9, so be careful with that. So the OH minus concentration is 10 to the minus 9th, okay, which is still larger than what we would have gotten if we had done it the old way. Okay, and then C, if the pH is 11, that means the pOH is 3. So the concentration would be 10 to the minus 3rd for the OH minus. Let's go to the next slide. So do all these the same way. So what I did was I rearranged that equation in part A to it. So start off with KSP equals Fe3 plus times OH minus to the third, and rearrange it to get Fe3 plus by itself, which is, so if you look at the third line, it's Fe3 plus equals KSP divided by OH minus to the third power. And then we know what KSP is, so we'll use that third row there in part A. We'll use that for all three parts, okay? So it's just going to be a different number going in for OH minus, that's all. Everything else will be exactly the same. So for the first one, we put in 10 to the minus 7th. For the second one, we put in 10 to the minus 9th. And for the third one, we put in 10 to the minus 3rd, and that's what we figured out before. And then just solve for Fe3 plus. When you do that, you're finding really the concentration of Fe3 plus at equilibrium, but that's the same thing as the solubility of the FeOH3. Right, and so the rest of this is just math. Okay, so there's a note there that says if you solve for x the usual way, you would get 10 to the minus 10. So anyway, let's go ahead to the next slide. Whoops. Okay, I accidentally skipped 2 slides. Sorry about that. So I won't be able to go through the problem ahead of time as I usually do. So anyway, this problem says the KSP for silver sulfate, which is Ag2SO4, is 1.2 times 10 to the minus 5th. Find the solubility of silver sulfate in each of the following. So this is a common ion problem. In other words, A isn't a common ion problem, so we just do it the same way we would ordinarily. But B and C are common ions. So in B, we have Ag+, which is common with the Ag plus in silver sulfate up at top. And in C, the sulfate is common. The only difference here is that instead of writing 0 plus X or whatever, you write whatever the number is. Like for the silver in B, you start with 0.1 plus X. And for C, you have 0.2 plus X. That's the only difference. So whenever you've got something like that, 0.1 or 0.2 plus X, you just neglect the X when you multiply. Let's go back to the top. Silver sulfate, Ag2SO4, we can write the equilibrium as that double-headed arrow 2 Ag plus SO4 2 minus, right? So the ice table, ordinarily for the silver would be 0 plus 2x is 2x, but in this case, for part B, it would be 0.1 plus 2x is 0.1 plus 2x, but we neglect the 2x. So that just reduces to 0.1. And then that would have to be squared because remember in the equilibrium expression, there's going to be a coefficient of 2 there, so you'd have 0.1 squared. Otherwise, you just do it the same way you do part A, which I'll come back to that. And then for C, for the sulfate, you would write 0.2 plus X, which 0.2 plus X is 0.2 plus X. Neglect the X, so it's just 0.2. KSP would be 0.2 for the SO4 times I believe it's 0.01. For the, let me just look down here for part B. So you're going to have 0.01 times, that would be for the silver, and that's because you square the 0.1 because of the equilibrium expression, the 2 exponent. So 0.1 times 0.1 is 0.01, and then that X there is coming from the sulfate. And then for part C, the equilibrium expression will be, for the silver will still be 0 plus 2x is 2x squared would be 4x squared. But for the sulfate, it would just be 0.2, and you neglect that x. So where it says 0.2 plus x, just forget the x. Multiply 0.2 times 4, and you get 0.8 x squared, and then set that equal to your KSP, which is given back at the top. It's 1.2 times 10 to the minus 5th. So just solve for x, and you get, for part C, 3.9 times 10 to the minus 3rd. For part B, 1.25 times 10 to the minus 3rd molar. And for part A, you would just do it the way we've been doing it. So you're just going to wind up with 1.2 times 10 to the minus 5th equals 4x to the 3rd, and solve for x. And when you do that, you get that x is 1.4 times 10 to the minus 2. Next slide. Okay, this one again is phrased differently, and so the reason I've included these is because it gives you a chance to see them stated in various ways. So here, what massive zinc sulfide KSP is given will dissolve in 0.3 liters of 0.05 molar zinc nitrate, and then don't worry about that last part, just forget that. So we're given the KSP, and we're trying to find the solubility for zinc sulfide. So the equilibrium would be zinc sulfide, double-headed arrow, zinc 2 plus S2 minus. The equilibrium expression will be KSP equals the zinc concentration times the sulfide concentration. However, we have some of the zinc already. So it's not 0 plus X for zinc, it's 0.05 plus X. And then for the sulfide, it's 0 plus X, which means we're going to wind up with 0.05 plus X times X. But if we assume that that first X is negligible, we just wind up with 0.05X equals KSP. And we're given the KSP, so that means that we can figure out what X is. When we do that, we're finding what we usually want, right? We're finding the molar solubility. Notice again, this is 1 to 1 to 1, but this time they're asking us for the mass. Look back at the problem statement, what mass? So we have to convert it to grams, and in this case, we have to actually multiply by the molar mass. So, for example, if the molar mass were 100, then we would have to multiply it by 100 to get it into grams. But then we're still not quite finished because they don't want it for 1 liter. So when we find the answer originally, we're finding it in moles per liter, but we don't have a liter, we have 0.3 liters. So whenever we get done with all this other stuff, then we just have to remember to multiply by 0.3. Next slide. And so here it all is. So I don't think there's really much point to just keep going over and over the same thing. We figure out about halfway down that the solubility is 5 times 10 to the minus 21 moles per liter. And usually that's where you'd stop, right? But in this case, they want the mass. So if we wanted the mass of 1 liter, we just multiplied by the molar mass, which it almost was 100. I just pulled that out of the top of my head. So it multiplied by 97, and it becomes 4.85 times 10 to the minus 19th. And that's in grams per liter. But we don't have a liter, right? We only have a 0.3 of a liter, so multiply by 0.3 to get your final answer. Okay, next slide. All right, this one is another one that's phrased differently. Now they want us to figure out if this is going to precipitate. Look at the two things we're mixing here. Usually you'd want to be sure that you know which one of these things could precipitate. So let's look at them, lead nitrate, and also we have sodium fluoride. Now, if you recall, fluoride isn't in any of our rules. So it could present a problem, right? But if you look at the other things that are there, beside the fluoride, what have you got? Na, which is always soluble, right? And also on the other one, you have nitrate, excuse me, which is always soluble. So there's only one possibility that could be a precipitate here, and that's if you mix the Pb with the F. Which that formula would have to be PbF2 because Pb is plus 2. All right, and then plus in this particular case, and I think that's usually what happens, is they ask you specifically, will PbF2 precipitate? So that kind of, you know, takes away the burden of having to figure this out. So I bolded the Pb and the F. I guess I tend to think of it more the way I said it the first time because of what we do in 1311. All right. So will it precipitate? So what we're going to have to do is we're going to have to figure out what the Q value is here. And then we'll compare it with the KSP. And we're given the KSP is 4 times 10 to the minus 8th. So how would we figure out what the Q value is? Well, we have to do it the same way we would be doing it for the K value at equilibrium. In other words, this PbF2. So start with that. So, I mean, it doesn't look like you would, but you do. You don't start with the other two. You don't start with the lead nitrate or the NaF. You start with the PbF2 because that's what we're concerned about. And then a double-headed arrow and then Pb2 plus 2F minus. That would be your equilibrium. KSP is going to be Pb's concentration, Pb2 plus, times the F minus concentration squared. So we need to figure out those concentrations. We can't just look at it and pull out those concentrations as given. Like, we can't just say that the PbNO2 is 1 times 10 to the minus second. The reason is because it's not going to be the same, because we're adding 100 milliliters to another 100 milliliters of something else. So what we have to do is find the number of moles for both of these things and divide by the total volume, which will be 200 milliliters or 0.2 liters. To find the number of moles, we would have to multiply for the PbNO3, and it would be the same thing for the other one. 0.1 liters times 0.01 moles per liter would be 0.001 molar. Next slide. For if you'll come down about a third of the way down, the lead turns out to be 0.001 divided by the total volume, which is 0.2 liters, which is 0.005 moles per liter. So when you multiply the 0.1 times 0.01, you get the 0.001 moles. For fluoride, it's 0.0001 moles, but they both then have to be divided by the total volume, as we said previously. So when you do that, you get 0.005 for lead 2 plus and 0.0005 for the fluoride minus. All right, and then to find the Q, we just want to square the F concentration, which is the 0.0005, and that's because of the equilibrium expression, which is kind of in the middle there. The 2 coefficient means we have to square whatever the concentration of F minus is. Well, what is it? It's 0.0005, which we figured out. So because we know what the number is, we just write it in there. So it's 0.005 for the lead times 0.0005 for the fluoride, and that one is squared, and we get, when we multiply all that, we get 1.3 times 10 to the minus 9th for the Q value, and then we just want to compare that with the KSP value, which is what? Well, look back at the problem statement. It's 4 times 10 to the minus 8th, which is actually larger than 1.3 times 10 to the minus 9th, which means that more of this stuff can dissolve, or to put it a different way, it won't precipitate, so no precipitate will form. Next slide. Oh, I'm sorry I did that again. So the problem is that if I hit the slide at all, it goes to the next slide, and then I can't get back. It won't let me go backwards. So I apologize that I keep doing that. Anyway, so again, we just have the answer right in front of us, but all we have to do for this problem, it says, consider the following table of KSP values, and then we're also given the formulas. Which one would have the greatest solubility? In other words, we just want to find the X's. So, for example, for calcium carbonate, which is the top one in that chart, but it's actually cadmium carbonate, in the answer choices, it's B. So they rearrange the answers, and that's something you'll have to watch for, especially on the final, because they'll do that. So you would expect the answers to match the way they're listed in the table, but they don't. So anyway, but just to do the one that's at the top, cadmium carbonate, CdCO3. Okay, so every time it breaks up into Cd2 plus CO3 2 minus. So it's 1 to 1 to 1. So we're going to wind up with KSP equals X squared. Okay. So if you don't see that, just do an ice table real quick. Just write it down, and you'll see it's 0 plus X plus. 0 plus X is X. 0 plus X is X. X times X is X squared, and that's going to equal your KSP. So just say X squared equals 5.2 times 10 to the minus 12th. Solve for X, and you're done. For the second one, though, it's going to be 0 plus X is X for cadmium 2 plus, and 0 plus 2X is 2X for the OH minus, and that has to be squared. So that would be 4X squared, which you multiply by the X for the cadmium, and you get 4X to the third equals 2.5 times 10 to the minus 14th. Solve for X, and that's going to be answer choice E. So when you do that one, cadmium hydroxide, 2.5 times 10 to the minus 15th. You get 1.84 times 10 to the minus 5th. So I'm reading S from part E. Right, so S and X are interchangeable. You can use either X or S. Anyway, just do all these the same way. So 3 of them are done the way the first one at top is done, it's just x squared, and two of them are going to wind up with 4x to the third power equals KSB. Just do that for all of them and find the biggest number, which in this case is going to be C, which is 2.14 times 10 to the minus fourth, and that happens to be calcium fluoride, right? Yes. Okay, so these shouldn't be a big problem. Next slide. Okay, I'll try to keep the pointer away from the slide this time. All right, this one is very straightforward. You don't have to really do any math. You can do this in your head. In which of the following aqueous solutions would you expect silver chloride to have the lowest solubility? So this is a common ion problem. So the more common ions you have, the less soluble. So remember, there were a couple of ways we can make something more soluble. This is the only way to make it less soluble. And there are sometimes when you would want to do that. So you're going to have AgCl breaking up into Ag plus Cl minus. So if you have either Ag plus or Cl minus, then that will reduce the solubility. So in A we have Ag plus, in B we have Cl minus, and also in D and E. In C we just have pure water, so that's out. We can take that off the table at the very beginning. So that's a violation of the rule that when you have 5 answer choices and one's different, that's maybe the answer, but it's not always. So anyway, that's off the table, so get rid of C. So what we have to do, and we can do this in our head, right? So for A, let's just do these one by one. We've already got some silver plus in A, 0.02 moles per liter. And when AgNO3 breaks up into in water, it will produce 1 Ag plus and 1 NO3. So we're only going to have 1 Ag there. So 1 times 0.02 is 0.02. For part B, for the Cl minus, we have 0.02 molar, but when it breaks up into water, it will be 0.02 molar for the barium because it's 1-to-1, but it'll be 0.04 molar for the chloride because there are going to be 2 of those for every BaCl2 that breaks up. So far we've got 0.02, 0.04 for D. It's going to just be 0.015 because there's only going to be 1 chloride, and same thing for E, it'll just be 0.02. So B is going to be the answer, 0.04. Let's turn to the next slide. And there you go. All right, so as always, if you have any questions about any of these or the ones that we still have to do, just please feel free to email. Next slide. For which salt should the aqueous solubility be most sensitive to pH? What you're looking for if you get this kind of a problem is the one that is the conjugate base of a weak acid. So if you'll check across the anions all the way across that row of answers, so you got Cl, NO3, Bri, and then F2. So in other words, which of the following acids would be a weak acid? So what I'm going to do is I'm just going to stick an H in front of these. So for A it would be HCl, for B it would be HNO3, for C it would be HBr, for D it would be HI, and for E it would be HF. Now which of those 5, or maybe there might be more than one, would be a weak acid? But it turns out there's only one, and that's EHF, right? So there's your answer. The one that's going to be actually sensitive at all to pH would be E, because the more H you add, the more H plus, then the more it's going to draw F minus out of the equilibrium, and that will actually increase the solubility. Next slide. Okay, so here is our answer choice, E, for the reason that I just mentioned. So for the other ones, A through D, they're all going to be conjugate bases, but they're going to be conjugate bases of strong acids. So if you try to stick an H plus on them, they'll just redissociate. Next slide. All right, and I think this is our last problem. All right, I don't really want you to spend too much time on this. This is a way you can increase the solubility, and we'll see that it does increase it a lot. Also in the one that you do that's after this one, that also will demonstrate how much it increases the solubility. So what we're given here is the thing that we talked about in the lecture notes. We start with Ag and Cl, and we want to build up Ag plus in order to get it out of the equilibrium. So the basic equilibrium is AgCl, double-headed arrow, Ag plus, Cl minus. So if we can get rid of either the Ag plus or the Cl minus, we can get rid of a product that shifts the equilibrium to the right. That means the solubility will increase, which you do want that to happen sometimes. So, but if we try to get rid of the Cl minus by adding H plus, it won't work because HCl is a strong acid. It'll just redissociate. So the only hope we would have would be if Ag plus could somehow be removed, and it turns out that it can. And we talked about this before. If we stick a couple of ammonia molecules around it, they kind of shield it from the other things that are going on, and they make what's called a complex ion. And then that complex ion is no longer Ag plus, right? It's Ag plus, but it has two NH3s around it. One on, if you want to think about it this way, one on top and one on bottom. So that's no longer Ag plus. So the way the equilibrium perceives that is, oh, we lost some of our product. We need to shift the equilibrium to the right. And it does. Okay, so the basic KSP is 1.6 times 10 to the minus 10th. And then when you stick on one NH3, that actually has a positive constant. That means it goes in the forward direction. So it's more stable that way because you're shielding that positive charge. And the K for that, if you only had one, it's 2.1 times 10 to the third. And then if you add another one to that, you get 8.2 times 10 to the third. So sometimes they'll talk about a formation constant. And to get that, you would multiply the K1 times K2, which would be about 16 times 10 to the 6th, or 1.6 times 10 to the 7th. So the Kf here would be what I just said, and then the KSP is 1.6 times 10 to the minus 20. To the minus 10th, but what would the overall K value, Kc value be for all of this? And the answer is it would be KSP times K1 times K2, which winds up being about 32 times 10 to the minus 4th, or 3.2 times 10 to the minus 3rd. Anyway, so we'll see that in a minute, but just multiply all three of those numbers together to get the K value for all of the stuff happening at once. Then what we can do is we can write the whole thing out, which is going to wind up being this. Ag plus plus Cl minus gives Ag plus plus Cl minus. And then also on the left-hand side, you'd have two NH3s. And on the right-hand side, instead of Ag plus, you would have Ag with two NH3s attached to it plus. So it's going to be just like the third thing you see at the bottom there. Well, it's going to be like a combination of the second and third row. So you'd have to have two of these NH3s to match up with one silver. Anyway, we're going to see that in a couple of slides. So it's not going to be a KSP expression. It's just going to be a regular Kc expression like we had at the very beginning. Next slide. All right, so don't worry about this slide too much, except just notice if you look at the top where there's the red star, the first one at top, it's just showing you there that if you have AgNH3 2, that it's much more stable than AgNH3 1, which in turn is much more stable than Ag. In other words, it will go, if you have Ag plus and you add NH3, it will go all the way to the left there on that row to AgNH3 2, because it's the most stable form. Come down now all the way to the bottom and look at what it says there. K1 times K2 in yellow equals 1.7 times 10 to the 7th equals Kf for formation. That's the bottom two. We just said that a moment ago. If you multiply all three of these together, which is on the next slide, you get the K. So let's now go to the next slide. And don't worry about the rest of the stuff on this slide. Also, you don't need to worry about some of the stuff on this slide. But so if you'll look at the top right where there's a yellow box, then the first blue arrow that comes kind of straight across to the left, there is our equilibrium. AgCl is what we're starting with. We're adding two NH3s double-headed arrow, and we wind up with AgNH3 plus Cl minus. All right, so let's think about what the ice table would look like, because they don't have it here. So just imagine that's written across the top of an ice table. So what would you have under it? Well, for AgCl, you'll have nothing. For 2NH3, we haven't done this really that much, but it would be when we first start off, we already have some of it, and it was mentioned in the problem statement that we started off with 10 molar NH3. So you would have 10 minus 2x. 10 minus 2x, and the reason it's minus is because it's on the left-hand side of the arrows. And on the right, you'd have AgNH3 plus would be 0 plus x is x, and then for the Cl minus, you would have 0 plus x is x. All right, so your K expression, not KSP, but your K expression will be products over reactants, which will be AgNH3 2 times Cl minus the concentrations of both, and then divided by the concentration of NH3 squared. Okay, but for the NH3 squared, we're going to wind up with 10 minus 2x, but for the other two on the right-hand side, we're going to just get x. So what this is going to end up being is x squared over 10 minus 2x. And that also has to be squared because of that 2 in front of the NH3 in the equilibrium. So if you'll look down, well, it's given right under that paragraph, K equals AgNH3 2 plus times Cl minus divided by NH3 squared. That's where the second red star is to the left. And then if you come all the way down below where that kind of like turquoise blue print is, substituting these concentrations into the equilibrium expression gives K equals 2.8 times 10 to the minus third, which is what we got when we multiplied all three of those other K's together, equals what we just said, which equals in turn x squared over 10 minus 2x quantity squared. And notice that all the way to the bottom red star at the very bottom right, notice that both of those are perfect squares, so we don't have to make any assumptions like we usually have to. So we don't have to assume that the 2x here is negligible. We can just leave it in. Since it's just a perfect square, just take the square root of both of them, and then take the square root of the k on the other side of the equation, and you'll get x over 10 minus 2x equals whatever the square root of 2.8 times 10 to the minus third is. And go ahead and solve for x, which becomes a very simple problem. So it shows it down almost at the very bottom. Square root of 2.8 times 10 to the minus third equals x over 10 minus 2x. So you just multiply both sides by 10 minus 2x. Then collect your terms, get your x's on one side and your numbers on the other side, and solve for x. And there's no tricks to it. It's very straightforward. And when you get that, you should get 0.48 molar for x. Okay, so what is that? So look back at your ice table. X was the chloride concentration, and it was also the AgNH3 2 concentration. And then to get the NH3 concentration, we have to take the 10 we started with and subtract 2 times x. So we have to take the 0.48 moles per liter, multiply it by 2, and then subtract it from 10. Why do we have to do that? Because we started out with 10 for the NH3. And again, that was given in the problem statement. So 10 minus 2 times 0.48, this is on the left in the yellow box, is 9.04 molar. Okay, so that finishes this problem. So don't let this problem bog you down too much. It's important, and it's important enough that I might ask it on a test, but it isn't that difficult. I think maybe the book tries to point out every little detail, and if you don't understand it, you can go back and try to read through all of this stuff, but basically what I've just said is all you need to know. Next slide. Okay, so we're done with this one. So this is for Monday, and that's going to be 13 April. And so we'll be doing chapter 19 on Wednesday, and that's going to be, we're going to attempt to do both the lecture notes and the work problems in just that one day. It's kind of a lot, so I'll probably have to abridge it quite a bit, but we'll see what happens.